Section 2.7 Ions and Ionic Compounds. The nucleus of an atom is unchanged by chemical processes, but some atoms can really gain or lose electrons. If electrons are removed from or added to an atom, a charged particle is called an ion is formed. An ion with a positive charge is a cation. A negatively charged ion is an anion. To see how ions form, consider the sodium atom, which has 11 protons and 11 electrons. The atom easily loses one electron. The resulting cation has 11 protons and 10 electrons, which means it has a net charge of positive 1. The net charge on an ion is represented by a superscript. The superscripts of positive 2 and positive 3, for instance, mean a net charge resulting from the loss of 1, 2, and 3 electrons respectively. The superscripts negative, negative 2, and negative 3 represent net charges resulting from the gain of 1, 2, or 3 electrons respectively. Chlorine with 17 protons and 17 electrons, for example, can gain an electron in a chemical reaction, producing the chloride ion. In general, metal atoms tend to lose electrons to form cations, and non-metal atoms tend to gain electrons to form anions. Thus, ionic compounds tend to be composed of metals bonded with nonmetals, such as sodium chloride. In addition to simple ions, such as sodium and chloride, there are polyatomic ions, such as ammonium and sulfate. These latter ions consist of atoms joined as in a molecule, but they have a net positive or a net negative charge. We consider polyatomic ions in section 2.8. It's important to realize that chemical properties of ions are very different from the chemical properties of the atoms from which the ions are derived. Although a given atom and its ion may essentially be the same, plus a few electrons, the behavior of an ion is very different from that of its associated atom. Predicting ionic charges. Many atoms gain or lose electrons to end up with the same number of electrons as the noble gas closest to them in the periodic table. Noble gas elements are chemically non-reactive and form very few compounds. We might deduce by this that it is because their electron arrangement is very stable. Nearby elements can obtain these same stable arrangements by losing or gaining electrons. For example, the loss of one electron from an atom of sodium leaves it with the same number of electrons as a neon atom. Similarly, when the chlorine gains an electron, it ends up with 18, the same number as the electrons in argon. We will use this simple observation to explain the formation of ions until Chapter 8, where we will discuss chemical bonding. The periodic table is very useful for remembering ionic charges, especially those elements on the left and right sides of the table. Figure 220 shows the charges of these ions relate to the simple way of their positions in the table. The group 1A elements, alkaline metals, form positive 1 ions. Group 2A elements, the alkaline earths, form positive 2 ions. The group 7A elements, the halogens, form negative 1 ions, and the group 6A elements form negative 2 ions. Many of the other groups don't lend themselves to such simple rules. Figure 220. Predictable charges in some common ions. Notice that the red stepped line that divides metals from nonmetals also separates cations from anions. Hydrogen forms both positive 1 and negative 1 ions. Group 1A, except for hydrogen, are all positive 1. Group 2A are all positive 2. Group 3A are positive 3. Group 7A are negative 1. Group 6A are negative 2, and Group 5A is negative 3. Noble gases don't form ions. Ionic compounds. A great deal of chemistry activity involves the transfer of electrons from one substance to another. Figure 221 shows that when an elemental sodium is allowed to react with elemental chlorine, an electron transfers from a sodium atom to a chlorine atom, forming a sodium ion and a chloride ion. Because objects of opposite charge attract, the sodium and the chloride ions bind together to form the compound sodium chloride. Sodium chloride, which we know better as a common table salt, is an example of an ionic compound, a compound made up of cations and anions. We can often tell whether a compound is ionic, consisting of ions, or molecular, consisting of molecules, from its composition. In general, cations are metal ions and anions are nonmetal ions. Consequently, ionic compounds are generally combinations of metals and nonmetals, such as sodium chloride. In contrast, molecular compounds are generally composed of nonmetals only, such as water. The ions in an ionic compound are arranged in a three-dimensional structures, as in figure 2.21 shows for sodium chloride. Because there's no discrete molecule of sodium chloride, we are able to write only an empirical formula for the substance. This is true for most other ionic compounds. Figure 2.21, formula of an ionic compound. The transfer of an electron from a sodium atom to a chlorine atom leads to the formation of a sodium ion and a chlorine ion. The arrangement of these ions in solid sodium chloride is an example of sodium chloride crystals. There's no actual molecule. It just goes on forever. We can write the empirical formula for an ionic compound if we know the charges of the ion. This is true because the chemical compounds are always electrically neutral. Consequently, the ions of an ionic compound always occur in such a ratio that the total positive charge equals the total negative charge. Thus, there is one positive sodium and one negative chloride, giving sodium chloride, one barium positive 2 and two chloride negative 2s, giving barium chloride, and so forth. As you consider these and other examples, you will see that if the charges on the cation and anion are equal, the subscript on each ion is 1. If the charges are not, the charge on the ion without a sign will become the subscript of the other ion. For example, the ionic compound formed from magnesium, which magnesium forms positive 2 ions, and nitrogen, which forms negative 3 ions, is Mg3N2.